coming back after this gap. We were discussing, we were studying some properties of the three-dimensional proper rotation group SO3, and we had looked at several ways in which the elements of this group can be parametrized. What I would like to do now is continue with that discussion. We were looking at some of the ways in which we can exploit this axis angle description. So I will do that again now. I mean, I will not repeat what we did last time, but I will look at another very useful result which comes from the axis angle description in a very nice way. And this is the description of equivalence classes in the group SO3. You remember that we have said that a general element of this group can be parametrized by a three-dimensional vector with magnitude not exceeding pi, and this covers the entire group. And suppose now, you probably also remember the expression. If one of you can dictate it to me, I would be grateful just to see that you are with me. What is the first term? Delta jk times cosine alpha, is that right? Plus 1 minus cos alpha over alpha squared alpha j alpha k minus sin alpha by alpha epsilon jkl alpha l. Okay. Now, supposing you take some other element b in the rotation group, we are working in the defining representation, and you ask for this element the result of conjugation of the element a alpha by some other element b. I don't write the axis angle parameters for b, they are not necessary. This is very easy to calculate. The left hand side is a product of three matrices. The matrix of B inverse is the transpose of the matrix of B, and you can plug in this A, the matrix A, and you can actually carry out this calculation. There are a couple of formulae which are useful, and since many of you are students and looking at these things for probably the first time, I want to go through this, sorry, I put an extra equality sign, shouldn't be there. Just for me to know who is familiar with these things and for whom this is new. Can you tell me what the right hand side is? There is a summation over K1 and K2 because they are repeated in this. Delta? J1, J2. This is just the expression of the orthogonality relation. Then, suppose I take three matrix elements and put in the Levi-Civita symbol, and now I sum over all three, K1, K2 and K3. What is this equal to? Huh? Epsilon? J1, J2, J3. So we say that the Kronecker symbol and the epsilon symbol are invariant tensors with respect to the proper rotations. So using those formulae, this can be easily calculated. And this I leave as an exercise. All that happens under conjugation is that the axis angle vector gets rotated. And this in my notes, it is equation number 27. All right. So conjugation acts very nicely in the axis angle description. It just rotates alpha to alpha prime. The element B of the rotation group acts on alpha and gives you alpha prime. So maybe I can rub out these invariant tensor relations. I rub this out also. So from here we can immediately see how the group splits up into disjoint equivalence classes. You can see that the only change is in the axis of the rotation, not in the angle or not in the amount of the rotation. That is to say, modulus of the vector alpha prime equals the modulus of the vector alpha. So here is a listing. So you can see that the angle parameter alpha is a label for equivalence classes. All rotations about whatever axis you like, but of a given angle, they will all belong to one equivalence class, one conjugacy class. So let us list them. This is the conjugacy class of the unit element that is always in a class by itself. Then I look at rotations by amount alpha, where alpha is strictly greater than 0, strictly less than pi. For each such alpha, I have an equivalence class. And what are the elements in this equivalence class? I can list them. I keep the amount of rotation fixed, and I allow the axis to go all over the unit sphere, S2. And then I must include the equivalence class made up of all rotations by pi about any axis. The only thing is that we have to see that in this third case, there is a double counting. So if you don't want to count twice, with each n, you take n over a hemisphere, but then there are boundary edge problems and so on. Anyway, you can see that the size of an equivalence class, it jumps discontinuously. It has one element here, it has a continuously infinitely many elements here, all the way from when alpha goes from 0 to pi. And when you come to the other end, it suddenly drops by 2 essentially. Okay? But anyway, this is the way in which the equivalence classes can be labeled. And if you ask, can you show me a representative element, a convenient element which represents each class, then one can manage throughout the range of alpha with, let us say, rotation about the z-axis. And this, you know what its 3 by 3 matrix is. I don't even have to write it. So here are representative elements for each of these equivalence classes. A class function, that is a function which has some value on each equivalence class, would be written as a function of an angle alpha, where alpha runs from 0 to pi, less than or equal to pi and greater than or equal to 0. So this is one very simple exercise which you see from the axis angle description. So this is an application of this description. The next thing I want to describe is the structure of this Coset space. Now, for this purpose, you remember how a general element can be described in the Euler angle language. I hope I am writing it correctly. You can check. and what are the ranges. You may please check that these are correct. Every element can be definitely written in the Euler angle description. It will not be unique, that part we know. So now the argument I am going to give now to describe what is called the Coset space. Now this should not be mistaken for a quotient or factor group. SO2 is a subgroup, but it is not an invariant subgroup. But you can just ask, take the group SO3, take any SO2 subgroup, for example, the subgroup of rotations about the z-axis, and consider all the cosets, let us say, I don't remember now, the right cosets I suppose, that's the notation I've introduced. Can you describe the space of right cosets in a nice way? In contrast to equivalence classes, you remember every coset is of the same size as every other coset. So this Euler angle description gives a hint. You can think of this third factor as running over a coset while you keep the first two factors fixed. That is, keep theta and psi fixed, allow phi alone to vary, you are going to run over a coset. So you can say this product of first two factors is a coset representative. So in this coset representative, see the way the angles have been introduced, they are a little unfamiliar compared to what we normally use in three-dimensional geometry. So please keep track of this fact. You can sort of guess that the space of cosets with respect to SO2 is the unit sphere S2. Now this is not a very good argument. What I have indicated here is not a good argument, but I just wanted to show it to you. It is suggested by the Euler angle description. There is a much neater way, much better way to do it, and that is the following. So anyway, this is true. The space of cosets of SO3 with respect to the subgroup SO2 can be identified with the surface of the unit sphere S2. A much better, good, proper argument to show this is the following. Take any element of the group, apply it to the unit vector, let us say in the z direction. What will the result be? It will be some unit vector lying somewhere on the unit sphere. Which vector depends on the choice of A. Now, take any other A, let us say A prime, which is in the same coset as A. If A prime and A are in the same SO2 coset, right coset I guess, that's our definition, they must differ by some rotation along about the z-axis by some angle phi. So this equation tells you every element of the rotation group leads to or uniquely determines some unit vector on the sphere S2. This unit vector is the same for all elements in the coset of a given element. Because an A prime and an A, if they are in the same coset, they must differ only in this way on the right. And this z-axis rotation applied to E3, what will it do? It will leave it invariant. So A prime and A, if they are in the same coset, map E3 into the same unit vector n on the unit sphere. So you can see in this way that there is a one-to-one correspondence, and it is global. There is no hitch anywhere, no singularity anywhere. Every SO2 coset determines a unit vector n on S2. Every n determines a coset in SO3. So this is a very important result. And one reason for my writing it is to warn you from this you cannot say that therefore should we not think that globally the rotation group has a structure of the Cartesian product of the subgroup SO2 and the unit sphere. This is not true. This is not true. This is true, and here it is not a quotient in the sense of group theory. It's not an invariant subgroup. It is a family of cosets. Set of all cosets of SO3 with respect to this subgroup, it is indeed S2. That does not mean that you can take this SO2 and swing it to the right. You cannot do that. You remember that, well, I leave it to you to argue why this cannot be true. We do know what SO3 is globally. It is S3 modulo identification of diametrically opposite points. That is the correct global description of the manifold of SO3. This is not so. This is not SO3. So you have to be sensitive to some of these global properties. You can't take the attitude, this must be almost correct, maybe there are one or two places where things go wrong. In fact, they do go wrong somewhere, therefore this is not true. Okay? Okay. Now, so we have had a good look at the group, the structure, the elements, the composition, the description, cosets, classes, all these things we have seen. I will leave it as an intuitively obvious fact, exercise for you to convince yourself apart from SO2 subgroups, there are no other continuous subgroups in SO3. Of course, there are any number of discrete subgroups, but continuous subgroups SO2 about some axis or the other, that is all. There are no other continuous subgroups. So no other interesting coset spaces to look at. Now let us look at functions on the group. So we have been looking at the group itself from various points of view. Now we look at functions on the group, how can they be described, and how can we talk of integrating a function on the group over the group manifold. So a function on the group SO3 may be real or complex, will be written as f with argument capital A, where A is a variable group element. So we want to define a normalized, non-negative average of such a function over the group. So we want to introduce an integration process, which I write symbolically in this way. I denote by dA a volume element in the group SO3, and the domain of integration is the whole group manifold, and we want to give a reasonable definition for this integration. It must have desirable natural invariance properties similar to what we had studied in the case of a finite group, and I will write the three invariances we would like the integration process to have. If you replace the element A by its inverse, the integral should not change. It should not change under left translation or under right translation for any fixed A0. And the other condition that we would say is that if I take the function which has the value 1 everywhere, this would be a normalization. It should be 1. then this integration can be this integral, the volume element, can be explicitly computed, and I am going to write the result for you, and I will leave it as a problem for you to derive the results which I am now writing. I will write these expressions in all the three ways we have learned to describe the elements of the group. I will write it in axis angle variables, I will write it in homogeneous Euler parameters, and lastly I will write it in Euler angle description. And these are all equivalent if I describe elements of the group by axis angle variables. Here is the expression for the invariant integral. So you can see, well, let us look at the expressions in the other two parameterizations also. The numerical factors are determined by this normalization condition. Remember that in the Euler parameter description, the group is pictured as essentially the surface, the unit sphere in 4 Euclidean dimensions, except that diametrically opposite points have to be identified. So a function on the group, real or complex, a function on SO3 can be regarded numerically, if you like, as a function of a real 3-dimensional vector, where this vector lies inside or on the surface of a sphere of radius pi. Since we are involved with integration and we will always deal with nice functions, no delta functions, if we can help it, we don't have to worry about the fact that on the surface, when alpha is equal to pi, a point and its antipodal point are the same group element. Yeah, that is true, but this is not going to cause any difficulty unless we put f equal to a delta function at one point and not at the opposite point. We shouldn't do such things. We must be reasonable. Similarly here, we can say a function on the group SO3 can be regarded as a function on the unit sphere S3 in 4 real dimensions, provided we agree it is even. That is, you take a point A0, A1, A2, A3, switch sign of all the components, the function has the same value at the diametrically opposite point. So that is understood. And then the third expression, which is important, is in terms of Euler angles. So depending on which parameterization you wish to use in any particular case, you must write f in terms of the appropriate variables. So I leave this as an exercise for those of you who may not have seen these expressions, derive these expressions. I will not give any hints, only one hint. This is a relatively easy thing to start from. It has to be something like this. This delta function enforces that you are actually sitting on S3, not all over 4-dimensional space, and it has all the necessary invariance properties. And once you check that this is correct with this normalization, from here you can easily go here, or from here you can go there. Okay? So there is no ambiguity. Everything is perfectly well defined. The fact that you are able to normalize this integral is a reflection of the fact that this is a compact group. That the function f, if it is set equal to 1, the integral is, you can say, the total volume of the group. And only if it is finite, can it be normalized to be unit volume? And the point is that the volume has to be measured in such a way that it is inversion invariant, left translation invariant, right translation invariant. Okay. So this is an interesting thing for you to actually get these expressions. Yeah, please. Yeah.
Coming to the last form.
Euler angle form.
Yeah. In terms of the Coset space representation you gave.
Yeah.
It's just the S2 and SO2 integration.
Yes. True.
That may help them to reinforce
Yeah.
the connection.
Right. In the notation I have been using, this is the SO2 part. These two are the S2 parts. Okay, because we agreed that cosets correspond one-to-one to points on the unit sphere. So integration over the group, the volume element, the domain of integration, it really looks like SO2 Cartesian product S2. But be careful, for integration, no harm as long as f's are not singular anywhere. But you must not jump to the conclusion, doesn't this suggest that the manifold SO3 is the product of an SO2, which is a circle, and an S2? It is not true. Okay? So be careful, though this might suggest such a thing to you. Now, supposing you have a function on the group SO3 which is constant over SO2 cosets. That is to say, I take a function which does not change its value when I move from the argument A to some other point in the coset of A. What does this mean? It means that in the Euler angle description, f is only a function of, so I say for all phi. This implies f is a function in the Euler angle description only of the first two Euler angles. It is independent of the third one. And for such a function, for such functions, the integration over the whole group, so these are for functions constant over each coset. What does it mean? It means they are functions over the space of cosets. Such functions are functions of only two Euler angles, and the average value collapses to the normal rotationally invariant integration over the unit sphere involving the solid angle. And here I just want to say the way we normally introduce theta and phi for problems on S2, the variables have got this little switched here. I have already used up phi for some other purpose, so this might look a little bit unfamiliar. So just get comfortable with the notation. Okay, so you can see how from invariant integration over the group we can come to, in a natural way, rotationally invariant integration over the unit sphere, and the solid angle idea automatically comes out. So this part is nothing but the solid angle, familiar solid angle over the sphere S2. Okay, so this much for functions on the group and their integrals. There is one very important construct which we use based on this notion of invariant integration. It is the Hilbert space of all square integrable functions over the group SO3, and I will define it here. It consists of complex valued functions for which the inner product of a function with itself in the Hilbert space sense is defined in this way, and our space L2 as the notation tells you consists of all functions which are square integrable over the group. Okay. So this is the Hilbert space which we use for several purposes. Within group theory, it is a space which carries the left regular representation of the group, the right regular representation of the group. It is also the Hilbert space of Schrödinger wave functions for what physical system? It is natural space, pardon? Hydrogen atom, no. Because rotations are important in the theory of the hydrogen atom, but this is not the space of Schrödinger wave functions for the hydrogen atom. It is a space of Schrödinger wave functions for another very natural physical system which you all study in classical mechanics also. Should I say it, or should one of you tell me? Jagannathan, is it a fair question? It is the Hilbert space. These are the wave functions which you will use if you want to describe.
Ask them for a classical mechanical system which has only 3 degrees of freedom, all are angular variables.
Ah, okay, you have asked. Why should I repeat? Yeah, answer his question. Rigid body. Which kind of rigid body? Moving about anywhere in 3-dimensional space? No. What is the restriction?
The center of mass is fixed.
Any point is fixed. Why center of mass?
Symmetrical tau.
No.
Any rigid body.
Any rigid body, whatever shape, whatever the moment of inertia tensor may be, any one point in the rigid body held fixed. That is a well-defined quantum mechanical system. Its configuration space. What is the configuration space of a classical rigid body with one point fixed? The rotation group. The point which is fixed need not be the center of mass, need not be the any special location, and the body does not have to be symmetrical in any way either, just has to be rigid. So you see that that's a natural physical system for which the configuration space is a continuous group. That's a very important idea, and a lot of very interesting things happen when you discuss classical mechanics and then quantum mechanics for a system whose configuration space is a Lie group. So here is a simple example. So this Hilbert space is important for us for two purposes. One, from representation theory point of view, we will come to it very soon, because it carries the left regular representation as well as the right regular representation. It is the important thing for quantum mechanics of a rigid body. And it is exactly what is used in the collective model in nuclear physics, where there is who are those people? Bohr and Mortelson, right? Junior Bohr, not the senior. Bohr and Mortelson, they got the Nobel Prize. Today is the Nobel Prize day. So they got it for their work on the what is called the collective model, collective motion in nuclear physics. I remember from my days when the mass number, capital A, is somewhere in the range 150 to 180 or so, then to a good approximation, the entire nucleus can be thought of as a rotating rigid body, and in the ground state it has an, what is it called, distortion. I mean, it's not spherically symmetric. It has a ellipsoidal shape. And so in that area of nuclear physics, wave functions for ground states, for states of nuclei, are things belonging to this Hilbert space. Okay. So what are all the things you have learnt about the group SO3 so far? How it is defined, how it is described, how the law of composition works, and then we have seen how we can describe functions, how we can describe cosets, equivalence classes. Fair number of things have been covered in this description, and we have come to this Hilbert space also. Now we launch into representation theory. Some important properties of SO3 representations. Here I will not be giving derivations of the statements that I am making. I am listing those properties which I think are important, which every one of you should try and appreciate, and find the proofs or the derivations in different textbooks available to you. Most of what I say will be found in any good text on quantum theory of angular momentum. So I leave it to your ingenuity to find a good book. So I will make several statements, discuss each one a little bit. Every representation is equivalent to and so may be assumed to be what? A unitary representation. This happens because this group, it's a continuous group, it's a compact continuous group. That is why the family of unitary representations exhausts everything. So it means that therefore we only need to find all unitary irreducible representations up to equivalence, of course, as far as representation theory goes. So these are the basic building blocks for all representations. The irreducible ones are the building blocks for all representations. So every irreducible unitary representation is finite dimensional. This is also a consequence of the fact that it is a compact continuous group. For example, for the Lorentz group, this will not be true. 3. It is a fact that there is one unitary irreducible representation. Always it is understood apart from equivalence in each odd dimensional space. And as you know, in quantum mechanics, the dimension is written as 2L plus 1, and since it has to be odd, L goes over integer values, and the representation itself is symbolically written as D superscript L and argument group element. And you can see the defining representation, which is where we started from. What does it correspond to? L equal to 1. That's the vector representation. So these are the important facts. Then 4. Every unitary irreducible representation can be brought to a real form. That means that the matrix is D superscript L of A, calculated in some basis. In general, they are complex. They are also unitary if you use an orthonormal basis. You can bring it all to real form by suitable choice of basis. So in a suitable orthonormal basis, all the matrices are real. However, in practical applications, certainly in quantum mechanics, it is more convenient to choose an orthonormal basis in which the representation matrices are complex, because in that form they have algebraically a simpler structure, somewhat easier properties. But in principle, every irreducible representation is entirely real. And the last I want to list, each unitary irreducible representation, except for, of course, L equal to 0, is faithful. That means that what is the representation L equal to 0? It's a trivial representation. It is one-dimensional. And in that representation, every group element A is represented by the number 1. So it's a representation, and it must be counted. It must not be disregarded. Must count it in the list of all representations. Leaving that out, every representation is irreducible representation is faithful. That is, distinct elements A not equal to B will imply D of A is different from D of B. The representations, non-trivial representations, preserve distinctness of elements of the group. Okay, so these, of course, there may be more properties which are interesting and useful, but I thought I will just list these 5. Now, depending on the way you parameterize the group elements, the representation operators or the representation matrices can be written in various ways. And if you, for some purpose, invent some other parameterization, you can use that as argument for D. So, whether the representation is reducible or irreducible, in general, we can write the operators of a representation for the rotation group in any one of these forms. What is always true, whatever representation you take, if you use axis angle variables, which is very convenient for certain purposes, then what I am writing now will always be valid. And I have given a number for this. If you take elements in the rotation group not too far from the identity, I don't tell you how far, sufficiently close to the identity, then the composition law of group multiplication will read like this. So this is a statement which will be true. This is why the axis angle description is particularly convenient to discuss such questions. If you try to write the content of this equation in Euler angle form, it will be a bloody mess. Sorry, I shouldn't use such words, right? It will be very, very messy, but it is quite neat in this form. And where does this come from? Remember, we had derived this from the defining representation for elements alpha and beta not far from the identity. And since that was the composition law of the group, it has to be obeyed in every representation. So this is a universally valid composition rule. Next comes the concept of generators of any representation. It is defined. Again, it is convenient to use axis angle variables for the definition of generators, and I do this because I don't think in most textbooks of quantum mechanics or quantum theory of angular momentum, not much attention is paid to this particular parameterization. But from the general theory point of view, it is extremely convenient. Okay, so given any representation, we know it is unitary, it can be assumed to be unitary. Whether it is irreducible or reducible, it doesn't matter. The generators of a unitary representation of the rotation group are defined by this rule. You look at the operators or the matrices D of alpha, for alpha very close to the 0 vector, expand it in a Taylor series. The coefficients of the linear term apart from this minus I factor are the generators of the representation. This I is a matter of convention. Mathematically oriented people will not use it, but because in quantum mechanics it is very convenient, and because it makes the definition of generators such that generators are Hermitian and Hermitian quantities are physically observable, etc., we will use the quantum notation. So now I am telling you some things which are true for the rotation group as a kind of preparation for what we will study in more detail, more comprehensively when we come to the general theory of Lie groups. So, in the case of the defining representation, L equal to 1, what are the generators? Do you remember? It was 10 days ago, 12 days ago, no, 10 days ago. We had used a certain notation for the generators of the rotation matrices in the defining representation. What was it we called them? Huh? We had used a certain letter for it. If I write it, you will remember. And we had, what we had given, that equation is the matrix element KL of Sj is minus I epsilon j KL. That defined the matrices. It is those matrices which are the generators of the defining representation. What are the generators in the trivial representation? Trivial representation means L equal to 0. So what are the capital J operators in that case? J1, J2, J3, what are they? Huh? All of them are 0. Because d of alpha is 1, the number 1, whatever alpha may be. So you differentiate, you will get 0. So for the trivial representation, identity representation, the generators are 0. For the defining representation, they are the 3 by 3 matrices which we had written down some time ago. For a general representation, that is the definition. Now, here is what happens. This is not difficult actually for you to verify. This composition rule of the group, the way that group elements multiply to give new group elements, and this definition of the generator of a representation, the two together, when they are suitably exploited, you find that the generators obey certain commutation relations. This square bracket on the left is the commutator of quantum mechanics, and epsilon is the Levi-Civita symbol. And what I am claiming, I am not going to prove it. It is not hard. You can prove it starting from here and using that. You have to do some amount of manipulation of the formulae, which can be done. What I want you, and we will see this later in the general theory of Lie groups. But the thing is that the expression of the group composition law for elements very close to the unit identity element is contained in a system of commutation relations among the generators. This is true for every continuous group, for every Lie group. The coefficients which appear in these commutation relations, they are called the structure constants of the group. So we can say the Levi-Civita symbol taken all together, all 27 components of it, constitute the structure constants of the group SO3. This is a notion I am just introducing here, just to prepare the way for later. What is important is that once the group is given through some defining representation or any way you like, a continuous group is given, once and for all, these so-called structure constants can be calculated and tabulated and written down on a sheet of paper. then you will find in any representation of the group, whatever the dimension may be, calculate the generators of any representation, their commutation relations will always read the same. Does not matter which representation you are talking of, as long as it is a representation of the rotation group, its generators will obey a standard set of commutation relations whose structure is determined by the group structure. So it's the commutation relations that are common to all representations, just as this composition law near the unit element is common in to all representations. One can go one step further. Here was the definition of the generators of a representation. One can integrate this, and one can show that for finite values of the axis angle variables, the matrices or the operators of a representation can be written in terms of the generators in this way, in the exponential form. So this is the convenience of the axis angle variables for the rotation group. As an example, it allows you to express the operator representing any group element as a single exponential. You are all familiar that if you use Euler angle description for the rotation group, the matrix, the operator or the matrix D for the group element with these three Euler angles, it is not a single exponential. It is a product of three exponentials. From the practical calculational point of view, this is very convenient. We will see in a little while. But from the general theoretical point of view, this is extremely convenient. So coordinate systems on a group, Lie group, which have this nice property that a group element can be described in a representation as a single exponential with the exponent involving the generators. They have a special name. They are called canonical coordinates of the first kind. Since I will define this later, anyway, I will give the formal definition later. Okay. So let me be a little bit careful here. If you know that you have a representation of the rotation group SO3, if you let us suppose you constructed it in some way and you were sure you have a representation, in a representation, here are the generators, here are their commutation relations, and here is an expression for the operators of the representation in terms of the generators. All these equations are valid. We will discuss them in a little while from a converse point of view. But I come to that after a discussion of the property of generators under any conjugation operation. Take the element with axis angle variables alpha, take capital A to be any other element, and carry out the conjugation. Here it is very easy. You can convince yourself. We had an equation earlier for this purpose. You remember that all that happened was that under conjugation, the rotation A acted on the axis angle parameters. Remember, that's how we listed the classes at the start of today's lecture. So that is the same statement I have made here. Now, since A is an orthogonal matrix, I can switch the action of A on alpha, replace it by the action of A transpose on the triplet of generators. Now, generators are operators, not numbers. Now you compare this and that, expand the two sides, keep the lowest order terms in alpha, and you will get this operator statement. This is an important equation. I give you its number. So it's very easy to derive. It says that you take the generators of any representation of the rotation group under conjugation by the representation itself. The generators always transform in a certain standard fashion independent of which representation they are generating. The generators always belong to what? The defining representation. So the defining representation is the representation to which generators always belong, whatever representation you are talking of. So that has a special name. It is called the adjoint representation of the group SO3. So let me jump a little ahead so the terms become familiar to you. In a general case, any general continuous Lie group, the representation to which the generators belong is always called the adjoint representation. The adjoint representation may not be the same as a defining representation for a general group. For the rotation group, many things coincide. The defining representation is the same as the adjoint representation. It is three-dimensional, given by real 3x3 matrices. So I have sketched for you some of the important properties of a unitary representation: the generators, their commutation relations, their transformation under finite rotations. What I want you to appreciate is that equation 41 I have written there, it is actually a result of integrating this commutation relation. You have to get a qualitative feeling for it. If you were to start with that equation 41, in the center are the generators and left and right are a general element, capital A. Take A to be close to the identity. See what 41 becomes when A is very close to the identity and A itself is written in terms of generators. It will boil down to the commutation relations. So the commutation relations they give the information about the adjoint representation nature of these generators. Now one comes to the converse way of looking at all these properties, and that is the following. Can I say that if I have found a set of matrices or operators in some dimensional space obeying the commutation relations, can I say that starting from there I can construct a representation of the group? This is the converse. I repeat, what we have seen up to now is if a representation is given to you, you can define generators, you can show that they obey these commutation relations, you can show this exponential form in axis angle variables, and you can also show the adjoint transformation law. All of these follow if you have a representation. Now the question is, can we exploit these relationships in the following way? If we have found a representation of the commutation relations, a solution to these commutation relations, if we found a set of three operators obeying these commutation relations, if we use them and say this is how we shall represent an element of the rotation group, will we have a group representation? Yes? A representation means globally it is a well-defined. For every group element there is a unique operator. They obey the multiplication rule of the group elements. From group representation, generators follow, commutation relations follow. This expression for finite group elements in terms of generators follow, because we are using nice system of coordinates here. This adjoint transformation law also follows. Now we ask the question in reverse. Can we say that, can we use these two equations as a means of constructing all representations? Is it enough to find solutions of the commutation relations? Will they have enough information in them to guarantee that if you then define d alpha in this way, that these will obey the composition law of the rotation group? Is all information about the structure of the rotation group contained or captured by these commutation relations? In other words, if this is true and if this is defined, will I find this to be true? Not only infinitesimally, but for all alpha and beta, with all the higher order terms, whatever they may be. The answer is no. What has to be done is the following. The answer is, if you want to take this as the starting point of the whole discussion, commutation relations as the basic thing, we have to make sure that, see, the commutation relations come from an examination of the multiplication rule for group elements close to the identity. These things don't know. If you go all the way to pi, it's supposed to be the same as pi in the other side. They don't know these things. That information cannot be expressed in commutation relations. The global topological structure, manifold structure of the rotation group cannot be expressed through commutation relations. Is this good news or bad news? Maybe the true current will come, displacement current will go. Huh?
The audio is working.
Yeah. Yeah. But I was thinking that if the regular supply comes back, then the AC will also come. Huh? Okay. So the situation is that, see, some of the statements I am making, I am not able to prove today. I am just telling you some of these things. As you study more, you will have to fill in these gaps in the whole story. But at least you know what it is you have to look for. What it is that has to be added to the commutation relations is the following. It is that if I use this definition to define the operator which I hope will represent a rotation by amount 2 pi about some axis, I want this to be the identity operator. If and only if this is satisfied, will I really have a representation in the proper sense of the rotation group. I want to get the equation number for this correctly. Okay. Now, this means to construct all representations of the rotation group. It is not a hopeless situation. Find all representations of these commutation relations. They are much simpler from the algebraic point of view than finding operators obeying the group composition law. Much easier. It's of course non-linear, but it is easier. So it says, find all solutions of this. Out of all of them, if you have succeeded in finding all solutions of the commutation relations, pick up the subset obeying this global condition. So the commutation relation plus this single global condition, which must be true for all directions of unit vector n, will guarantee that you have a representation of the rotation group. Okay? So commutation relations capture the structure of the rotations near the identity element. This has to be added to make the picture complete from the global point of view. Now here is another. It turns out, and many of you may know this, essentially, if you have found all the irreducible representations of the commutation relations, essentially half of them will survive this condition, the other half do not. So only every other solution of these commutation relations, irreducible solution, will obey this global condition and will lead to a representation of the rotation group. And there is a reason for this. Now, sometimes I will make statements for which I myself don't know the proof. And if one of you here knows it, you may like to add some.
Before we erase, I just wanted to make a comment.
Yeah.
I will wait until your lecture is over.
Oh, no, please.
When you
Which one?
talked about this adjoint representation.
Yeah, should I write that back?
Yeah, I think that it may be useful.
Yeah.
Yeah. Now, see, at that point,
Yeah.
actually, you call it for some beginning students, you went a little fast.
Ah,
That you call it adjoint representation, but
yeah.
I mean, I just wanted to emphasize that it is a representation is something that has to be accepted. Because
That this is a representation.
yeah, that equation actually gives a,
Here it gives a representation.
yeah.
Yeah.
See, A is a point in the group manifold.
Yeah.
I mean, but dA is
Yeah.
something corresponding with point in the group manifold.
Yeah.
And then this equation actually properly defines a representation. That I think students will have to
Okay.
verify. I mean, only after it is a representation, it
Yeah.
accepts the name adjoint representation.
I agree. Actually, it happens to be the defining representation in this case. This is a 3 by 3 matrix A. What you're saying is, now you conjugate the left-hand side with dB, this whole thing, dB inverse for some other B. Then what will happen on the right-hand side? Calculate it. Show, as he says, that this consistency of this statement implies that on the right-hand side, you're dealing with certain specific representation of the rotation group, and it is the representation to which the generators belong. Whatever the generators may come from, whatever representation they may come from, they always belong to a particular representation. In the case of the rotation group, it happens to be the defining representation.
Could I ask that question, please?
Yeah, sure.
Can you use an example where the converse question actually arises, that you are having the commutation relationship, and then
Huh.
any example where?
Yeah, later in this section we will see. I am, see, some of these statements, it is as important that you are aware of certain facts as being able to prove them or demonstrate them. Sometimes knowing is good enough from the application point of view. The analogy is that, well, I don't know how to ride a bicycle, but those of you who know how to ride a bicycle, you know how to ride it. You don't know how it happens, right? The physics of it, it is built into your reflexes. You know it. Isn't that true? So it is something like that. So here, what I want to stress is that, so here I am making a connection. I am not able to prove it now. I may not be able to prove it even later. But you must know it. The reason why for the rotation group, solving the commutation relations is not enough to produce a group representation. What is the reason? Huh? The reason is the rotation group is not simply connected, it is doubly connected. We have seen that topological property some time ago, that you have two classes of closed loops in the case of the rotation group. One class consists of those which never exploit this opposite point property, or exploit it an even number of times. The other class consists of those which exploit that property an odd number of times. And a loop of one class cannot be smoothly deformed into a loop of the other class. Now, don't ask me why and so on. You have to, this is a major challenge for those of you who are interested. That topological property, that it is not simply connected but doubly connected, that is the reason why all representations of the commutation relations do not lead to group representations. And it is a fact that it is doubly connected that results in roughly half of these representations leading to the representation of the group. Okay? Yeah.
Ask a question.
Yeah, yeah. Yeah.
You have given a remedy for a trouble that could come, namely,
Yeah.
you want to pick only those things which can to be identity at 2 pi. Now, suppose you did not know the remedy, what is the worst that can happen? Maybe things will become identity only at 4 pi.
Yeah. But why are you sure they will become identity at least at 4 pi?
No, I am anticipating your next lecture.
Correct, I agree. So, this causality is violated a little bit here. Later we will be discussing a related group called SU2. I will put it in this way, and this is a hypothetical world. Suppose this rotation group SO3 had not been doubly connected. Suppose it had been simply connected. Suppose that every closed loop could be shrunk to the trivial loop. If that had been so, we would not have had this problem. Every representation of the commutation relations would automatically, upon exponentiation, give a pakka group representation. But this is like Niels Bohr once saying, this hypothetical argument, you say, suppose 2 plus 2 was equal to 5. All the economic problems of the world could have been solved. So it's like that. I'm just dramatizing it. The cause of this losing half the representation is the non-simple connectedness of the rotation group. So, if you want to understand it more, you know where to go look for the reason behind these things. Is that satisfactory, Simon sir?
Yes, sir.
So, I'll just go a few minutes and then stop. So, I will now just begin on a brief review of the irreducible unitary representations of the rotation group. And what is it we will do? We will just exploit what I have just been telling you. We will find we will borrow all the known irreducible representations of the commutation relations. We will retain only those which obey that global condition. That gives us all irreducible SO3 representations. So, for this what do? I will use the known results of the quantum theory of angular momentum. I am not going to derive that here. If this is something you have already studied, well and good. If not, then when you study quantum theory of angular momentum, there will be a well understood goal towards which it is going, namely to give a justification for the statements I am going to make. So, what is it that we are trying to do? We are trying to find all possible irreducible solutions for 3 operators J1, J2, J3. They must each be Hermitian and they must obey these commutation relations. Commutator J1 with J2 should be IJ3 and cyclically permuted. So, you are all familiar with the fact that if one defines something called the square of the angular momentum, total angular momentum, it has this property of commuting with every component of J itself. So, this, as you know, is called a Casimir operator. This J squared is called a Casimir operator. And this name is after a man, what is his initials? HBG Casimir. Huh? HGB Casimir. in later life, this was in the early part of quantum mechanics. Later he became a very big industrialist in the manufacturing company of Philips in Holland, Philips company. And this word Casimir, it is named after him, this Casimir operator, and this name is used in pure mathematics also, as far as I know. Casimir operator, that is the word they use. So, by Schur's lemma, you can convince yourself, because we want an irreducible representation, and because J squared has to commute with everything, J squared has to be a multiple of the unit matrix. So, the fact is as follows. So, here no derivations. For every integer value of little l, 0, 1, 2, etc., there is a representation of the commutation relations of dimension 2l plus 1. This is a fact. And what does the representation look like? Sorry, this equation is 44. What does the space of the representation? So we can say representation number L. So in every odd dimension, there is a solution of the commutation relations, and I am retaining only those solutions which obey the global condition. So I am dropping half the solutions of the commutation relations. Now, if you look at the commutation relations, you can convince yourself in the language of quantum mechanics that total J squared and the third component, let us say, of J3 form a complete commuting set. Actually, J squared can be dropped because it's a multiple of the identity. It has no variation among the vectors of the representation space because we are dealing with an irreducible representation. So J3 by itself, by convention, is chosen to be the operator whose eigenfunctions give you an orthonormal basis. And so the basis vectors in the standard notation are written in Dirac form as ket vector L comma M, and you know that the range of M is L, L minus 1 up to minus L. So it goes over 2L plus 1 values, and here are the most important properties. I will just write these equations and then we will stop for today. This is an orthonormal basis which can be chosen for the space of an irreducible representation of the commutation relations. J3 is diagonal, and instead of giving the matrix elements or the actions of J1 and J2 on these basis vectors, it is more convenient to deal with the complex combinations J1 plus ij2 and J1 minus ij2. The total J squared is a multiple of the unit operator, and the only equation we have to include is that we have here an orthonormal basis. Okay, so I'll derive. So this is what you get from the quantum theory of angular momentum, because in that quantum theory of angular momentum, one actually goes through the detailed process of solving the commutation relations, and here is the result. We have added this condition that 2 pi rotation about any direction, any axis, must amount to no rotation. What does it mean? The eigenvalues of J3 or J1 or J2 or any n dot j for a unit vector n must be what? What's the condition on the eigenvalues of, let us say, J3 from the global requirement? The eigenvalues must be integer. 2 pi rotation must not cause any change in the vector on which it operates. And from here you can see something. In this standard orthonormal basis, the matrix of the generator J1, remember J1, J2, J3 are all Hermitian. That is the way we find the representations. What can you say about the matrix representing the generator J1? Of course it is Hermitian. Can you say anything more in this basis? How will you get the matrix of J1 starting from here?
Add and divide by 2.
Yeah.
Add the these two matrices and divide
Exactly. Take this equation, two equations, just add them. Then J2 will drop out. What is the result? What can you say about the result?
by 2.
It's real. And therefore, it is symmetric. So J1 is represented by a real symmetric matrix in this standard description. J2 is represented by pure imaginary antisymmetric in this representation. J3 real and diagonal and non-degenerate. Okay. So this is a characteristic of the general representations, and maybe I stop at this point. Okay. So you have learnt quite a few things about SO3 in this way.